All right, guys. So in this lesson, we're going to go over all the different little things you need to know about the periodic table, different element classifications, and what is the normal charge that this ion has, or like when lithium forms an ion, what's its normal charge? When oxygen forms an ion, what's its normal charge? How many valence electrons some of the elements have? What the different blocks of the periodic table, the different groups, the difference between a group and a period, the representative elements versus the transition elements, the transition metals versus the intertransition metals, different things you need to know about the different regions of the periodic table and some of the different elements of the periodic table. So it's covering a lot of information, but it's not difficult information. It's just information that you have to spend time to memorize. But once you know it, then it's pretty straightforward. And also understand, like as I go through this lesson here, you're going to have a bunch of little periodic tables that are labeled differently. Okay, like so here it tells you some different things. Here we got more periodic tables, they're labeled and that kind of thing. But understand, whenever you take a test or a quiz in the class, this is what you get. You get this periodic table. So, you have to know that these are the halogens, and these are the noble gases, and these are the alkali metals, and these are the alkaline earth metals, and you have to know that these are the transition metals, and down here are the intertransition metals. We also call this the D block, and we call this the F block, and we call this over here the P block, and we call this over here the S block. Helium is a part of the S block. Helium's in group 8A, so it has so you might think it has 8 valence electrons, but no, helium only has 2 valence electrons, but the rest of the noble gases in this group have 8 valence electrons. And then because this is 7A, all these elements have 7 valence electrons, and 6A, 6 valence electrons. So all these little things you have to kind of memorize, okay? So this is what you get. You don't get the labeled periodic tables that I'm using for this lesson. You have to be able to retain the information that we talk about in this video and all the guided notes and all the periodic tables that we labeled in class. You have to memorize that so that when all you have access to is this, you understand how to use it, okay? So, you got to take some time. It takes some practice, repetition, look at it a few times every single day. Do that for a couple weeks, and then you'll have it memorized, and you won't have to worry about it. But if you just look at it now and then you don't think about it for another week, you're gonna have to relearn it that the next time you look at it. And then if you wait another week to look at it, then you're gonna have to relearn it again and again and again and again. So you got to do a little bit every day. Okay. All right. So let's jump into it. Okay. So first, understand the way the periodic table is set up. We put the elements in order of increasing atomic number, and that would be, number of electrons, number of protons in the nucleus, right? But also remember that atomic number is also number of electrons when we're talking about electrically neutral atoms. So so let me zoom in on this periodic table here, right? The atomic number for oxygen is 8, so that means 8 protons in the nucleus of an oxygen atom, but it also means that an oxygen atom has 8 electrons, okay? An oxygen ion has 10 electrons, but atoms are electrically neutral, so an atom of oxygen, that atomic number means 8 protons, but it would also mean 8 electrons, okay? Now, some students think that when first asked this question that the periodic table is in order of increasing mass. And for the most part, that's true, but there's exceptions to that. So the real answer is it's increasing atomic number, okay? So if we look, here's one exception to the increasing mass. So for the most part, as we go left to right and down the periodic table, the elements become more massive. But if we look at here, if we look at beryllium and iodine actually has a smaller average atomic mass than beryllium. But iodine is to the right of beryllium because it has 53 protons versus 52 protons of the beryllium. So it's not always the case that it's increasing mass. So don't make that mistake, okay? All right. So the very first thing you really want to know are where the metals are and where the non-metals are. Okay, and another thing to understand is how the periodic table is set up. So it's not just increasing atomic number, right? The elements are in the same vertical column because they react the same way chemically. So meaning they have, and the reason why they would act the same way is because they have the same number of valence electrons. Okay, so I know the atoms over here in this group react the same way, the atoms over here in this group react the same way, or similar way. Atoms over here in this group react the same way, and so on. So these elements react one way, these elements react another way, and the reactivity is based on what type of element they are, right? So the main thing is, are they metals or non-metals? Now, there is that category of metalloid, which we're going to talk about in this unit, but really for moving forward, when we get to Unit 4, Unit 5, Unit 6, it's really just going to be, hey, is it acting more like a metal or is it acting more like a non-metal? And the definition of metal versus non-metal, metals lose electrons when they react, and non-metals either gain or share electrons when they react, okay? And another way to think of metals and non-metals is if something is classified a metal, it has a certain set of properties, it does certain things, and something that's classified as a non-metal pretty much does the opposite. It has the opposite types of properties, right? It's not always the case, but that's kind of a way to think of it. Like non-metals are opposite of metals, or metals are opposites of non-metals. So if you know metals do that, then non-metals would do the opposite of that, okay? And so when we talk about metallic character, as we go left to right across the periodic table, what we're going to notice is things that act more metallic are to the left side, and as we go from left to right across the periodic table, now things transition from acting as metals to acting like non-metals. But it's not just straight across left to right. The trend for metallic character versus non-metallic character is on a diagonal. So the most metallic metal is francium, and the most non-metallic non-metal is fluorine. So as we start in the bottom corner, left-hand corner of the periodic table, and we go from left to right, we're transitioning from most metallic in character towards most non-metallic in character. And the reason why the noble gases aren't included in this is because we're talking about the reactivity of them, and noble gases don't react. So by reactivity, it means, you know, a non-metal is going to be the most reactive non-metal if it's the best at gaining electrons. And it turns out fluorine is the best at gaining electrons. And we're going to learn about why when we get to different periodic trends. Okay. Metals, the definition is that they oxidize, they lose electrons when they react. So the metal that gives up electrons the easiest would be the most metallic, and that happens to be francium. And again, we're going to explain why later. Just right now, understand, if you're talking about which metal is more metallic than another, well, notice that metallic characteristic is going to increase going this way. So if I'm further down to the left on the periodic table, I'm more metallic, and I'm further up and to the right on the periodic table, I'm more non-metallic in character, okay? So remember, let's go back to your periodic table that you get. Remember, you have this staircase that kind of separates the metals over here to the non-metals, and it tells you kind of that direction. Okay, it says metals are this way and non-metals are that way. Okay, and remember, the metalloids kind of fall along the staircase. Now, it's not every element that's on the staircase is a metalloid. Like aluminum is a metal, it's not a metalloid, but silicon is a metalloid, boron is a metalloid, germanium, arsenic, antimony, they are all metalloids. Okay, but again, that whether or not they're a metalloid or a metal or non-metal, it really, the metalloid thing isn't that big of a deal. What is important is, hey, if I'm on this side of the staircase, the left side, I'm probably going to act more like a metal, so thinking losing electrons. And if I'm on this side of the staircase, I'm going to be more of a non-metal, meaning either gaining or sharing electrons. So arsenic, yeah, it's a metalloid, but when you're thinking about how it's going to react, you're going to think of it more as a non-metal. But germanium, when you're thinking about how it's going to react, you're thinking it more of a metal, okay? Moving forward, okay? So let's get back to our lesson notes. Okay, so again, memorize the metalloids, and then anything to the right, non-metal, anything to the left, metal, except for hydrogen. Just remember hydrogen is a non-metal, okay? But notice that most of the elements are classified as metals, okay? All right, the next thing we're kind of responsible for are knowing a couple of the groups on the periodic table. Now, groups are also referred to as families, okay? So it's kind of the same thing. And so when we say group on the periodic table, we're talking about a vertical column, so up and down, okay? So this would be group 1, group 2, this is group 3, group 4, group 5, group 6. Now, I know this says group 3, even though this is the third column on the periodic table. This is group 3 of the overall periodic table. This right here, boron's group, this is where boron would be. This would be group 13 of the overall periodic table, but it's 3A because only these two columns and then the columns over here are the representative elements, are also called the group A elements. So a lot of times we'll say, instead of calling this group 13, we'll call it 3A. Instead of calling this one group 18, we'll call it 8A, okay? And that'll be important when we're talking about valence electrons here in a second, okay? But the main thing is, if we're talking about group, we're talking about a column, and there's 4 groups you have to know the names of. We call some of these groups different names. So we need to know the alkali metals, the alkaline earth metals, the halogens, and the noble gases, okay? And it's pretty easy to memorize, and the only ones that you're really responsible for naming in terms of group name are these 4, and it's the first 2 groups and the last 2 groups. So it's this group here, and then if we go to the last 2 groups, this group here and this group here, okay? So the alkali metals are the first group. Now notice that hydrogen is not filled in. Remember, hydrogen is a non-metal, so don't call it an alkali metal. The alkali metals start with lithium. So the first alkali metal isn't hydrogen because it's a non-metal. The first alkali metal is lithium. So lithium, sodium, potassium, those are alkali metals. And remember, we talked about it in class, but alkali means basic. And the reason why they're called the basic metals is because when you add them in water, the resulting solution has a pH above 7. And we'll get into the chemical reaction that's causing the pH to go above 7 and what that really means, what's going on in the solution. We'll talk about that later on this year. Okay, just right now, just, you know, that term alkali is just another way to say basic. Okay, pH above 7. Okay. Then we have the alkaline. Now, this periodic table that I chose to copy from Google says alkali earth. It's really alkaline. So alkali metal and then alkaline earth metal. But again, that term alkaline means basic. So these metals kind of do the same thing. Just these metals are more reactive, right? Because they're further to the left, so they're the more reactive metals. These guys react violently with water, produce a lot of heat, and sometimes will catch on fire, okay? But the alkaline earth metals, they react similarly with water. They produce a basic solution. That's why they're called alkaline metals. But they will, they don't react as violently, okay? And then we can switch it all the way over here. So fluorine's group are the halogens, okay? And the last group on the periodic table, these are the noble gases, okay? All right. Another thing we want to know is the representative elements. Now, the representative elements are the ones we're going to spend kind of the most time on talking in chemistry. And it's really going to be, you know, it's not going to be all of these down here. Like these representative elements, we're not going to really talk. Maybe, when we had nuclear chemistry back in Unit 2, we might talk about these because they're radioactive. But we really only focus on kind of like this kind of chunk here. We don't go way far down the periodic table. Now, we will do some stuff with these, but it's mostly the first 2 columns completely, but then on this side over here, it's really just kind of like that chunk that we'll really focus on. Now, we need to know what's going on here and what's going on down here and this, but let's just talk representative versus transition. So the transition elements are the ones labeled in gray. So remember, we call this block the D block, or we also call these the transition metals, and we call these the inner transition metals. So those are the transition elements, okay? These are the transition metals, these are the inner transition metals. And they're called the group B elements. The group A elements, which are the representative elements, are the ones highlighted in green. And let's go ahead and include the noble gases as representative elements. And when we label their group numbers, remember, like I said before, above boron on a regular periodic table, it'll say group 13 because it is the 13th column on the periodic table. But it's also 3A. It's the third group of the representative elements. So group 1 of the representative elements, group 2 of the representative elements, group 3. And the reason why that's important is because it's an easy way to know how many valence electrons something has. If you're just talking about the representative elements, okay, whatever group number they're in terms of group A, so 3A, 4A, 5A, 6A, 7A, 8A, that's how many valence electrons they have, right? So I know oxygen, I know sulfur, I know selenium, they each have 6 electrons because they're in group 6A. I know boron has 3 valence electrons, aluminum has 3 valence electrons, gallium has 3 valence electrons. Why? Because they're in group 3A. I know all of these guys over here have 1 valence electron because they're in group 1A. The one exception to that is helium. Remember, helium only has 2 valence electrons, but the rest of the noble gases that are in 8A, they have 8 valence electrons. Okay? All right, so again, we got our transition metals, the ones in blue. We got our intertransition metals, the ones in red. And then we got our representative elements. Now, this periodic table is calling it the main group because it's the ones we really focus on in first-year chemistry. First-year chemistry in college, mainly the representative elements, okay? You really don't get to the heavier transition metals and stuff and intertransition metals until you get to like inorganic chemistry, like advanced inorganic chemistry in college. You don't really focus on the chemistry of the transition metals until then. Okay, so again, our main focus are going to be the transition elements. So when we talk about the octet rule, that's really just for the transition elements. Like things want to have 8 valence electrons or 2 valence electrons. That's really mainly for the representative elements. The transition metals can do some funny things to get a more stable electron configuration, which we're going to talk about here in a little bit. All right. So again, 1A, 2A, 3A, 4A, remember we label those so we remember, oh, if I'm in this group, I have 8 valence electrons. Not 2 for helium, but or 2 for helium and 8 for the rest of the noble gases, but you know, the halogens have 7 valence electrons. Oxygen group has 6 valence electrons, right? Carbon's group has 4 valence electrons, okay? Now, the other thing we need to know are the blocks of the periodic table, and this is going to help us with what we call electron configuration, which we're going to talk about towards the end of the unit. But there's 4 blocks, the S block, the P block, the D block, and the F block. So the first 2 columns on the periodic table, that's the S block. So the alkali metals and the alkaline earth metals, and then also hydrogen and helium. Notice helium's over here, but it's part of the S block, okay? Then from like boron to neon and down this square right here, and it goes all the way down, right? It goes all the way down to OG. That's the P block. And then we got our transition metals, which is called the D block, okay? And then our intertransition metals down here, that's the F block, okay? Another thing we want to know are just have a basic understanding of what the elements are. Again, not in compounds, but when the elements are elements and they're just sitting there resting, not reacting with anything, and they're just in their elemental state, what state of matter are they? And the vast majority of the elements are solids. There's only 2 liquids. All right, so at room temperature, mercury is a liquid. It's a metal, but it's a liquid. Bromine is a nonmetal. It's a liquid, okay, at room temperature. So don't get confused that mercury being a liquid doesn't make mercury a metal. It's a metal. Mercury is a metal. It's just the only metal that is not a solid at room temperature. It's a liquid, okay? Now, there's a handful of gases, right? So we got hydrogen is a gas. Then we got nitrogen, oxygen, fluorine, chlorine. Those are gases. All the noble gases. Go ahead and include OG, okay? Call that a gas as well. It's a noble gas. It's probably a gas. It's probably just not enough information out there to confirm. These elements down here, the ones that aren't like on the periodic tables in our classroom and stuff like that, these are made in laboratories and they don't last long. So we really don't know much about them, Okay, so if you want to, go ahead and include Og as a gas in the noble gases. You're not going to be asked questions about that. Okay, but again, notice everything else, like all the transition metals except for mercury are solids. All the intertransition metals are solids. So it's good to know what their state of matters are, because the way the particles move will change the way things react with each other, right? So solid particles, they can just vibrate. So, maybe not as reactive as things that are in the liquid state that can move around a little bit more, and maybe not nearly as reactive as gases who are zooming around. Okay, so knowing their state of matter definitely matters when you're trying to predict, how is this going to react with that at this temperature and this pressure and that kind of thing. Okay. All right, so another thing that we need to discuss are the dot structures, and it's really just the dot structures of the representative elements. And what the dots in the dot structure represent are the valence electrons. And so remember, we know how many dots or how many valence electrons we need to draw in a dot structure based on group. So 1A, I need to draw 1 dot, 2A, I need to draw 2 dots, 3A, I need to draw 3 dots, 8A, I need to draw 8 dots except for helium, which is only 2 dots. Okay. And the way you draw a dot structure is you draw the chemical symbol of the element and you put the dots around the sides of the chemical symbol. And think of the chemical symbol as having 4 sides, and you don't want to pair up the electrons, and you can fit 2 electrons per side, so you can fit a maximum of 8 electrons, like over here. But they don't want to be paired up until they have to. So you can draw them a little bit differently than the way they're drawn here, but like nitrogen has 5 valence electrons, you should go 1, 2, 3, 4, and then 5. Right? Don't pair them up until they have to. Notice when you have 4 valence electrons, none of the electrons are paired up, right? You don't get any paired electrons until you have 5 or more valence electrons. So like lithium, you just draw 1 dot. Beryllium, you draw 2 dots because it has 2 valence electrons. And notice they drew them on opposite sides, because what we want to start to really think about is electrons repel each other, okay? So they don't want to pair up until they have to. Right, until there's no other spot for them to go. And they like to be as far away from each other as they possibly can. So if I only have 2 dots, go ahead and put them 180 degrees apart. You could put 1 dot here and 1 dot here, but again, if they could be spread out 180 degrees, that's the better representation, okay? So notice like nitrogen has 1 pair of electrons and 3 unpaired. But then when you have oxygen, now we got 2 pairs of electrons and 2 unpaired electrons. And then the halogens have 3 pairs of electrons and then 1 free electron. But then once we get to the noble gases, now we have a stable octet of electrons, of valence electrons. And because they already have that 8 valence electron shell as their outside shell, their valence shell, they don't react, okay? But this is how we draw our dot structures of the different elements. And again, how many dots? It just depends on how many valence electrons. Well, how many valence electrons does it have? It depends on what group it's in, right? If I'm in group 7A, I got 7 dots, 7 valence electrons, so I draw 7 dots around my chemical symbol, okay? And we'll just keep on rolling, okay? So another thing we need to know about are the ions of the periodic table. Now, if you think about it, right, the goal is to get to the same electrons as the noble gases. So like fluorine is just one dot away to have that dot structure, right? So fluorine needs to gain 1, chlorine needs to gain 1, bromine needs to gain 1. And that's why when they become ions, they only gain 1 electron, so they're only 1 minus. So everything here is 1 minus, right? But like something like oxygen, right, or sulfur, they need 2 more dots. They need 2 more electrons to get to there. So they have to gain 2 electrons. So they're going to be -2. And then remember, these guys have to gain 3 electrons. So they're going to be -3. But then we'll skip carbon's group for now and we'll go to aluminum's group. Instead of aluminum gaining 5, right? So aluminum could gain 5 to get like argon, or it could lose 3 and then have the same subshell underneath the 3 that it loses as neon. So it can lose 3 to get to neon, or it could gain 5 to get to argon. You don't want to lose or gain too many electrons. So aluminum, instead of gaining 5 to get here, it's going to lose 3 to get there. And so it's going to lose 3 electrons, and that's when we get a positive ion, and this one would be a positive 3 ion, right? So all the ions in this group are positive 3, all the ions in this group, because they have to lose 2 electrons, are positive 2, and all the ions in this group, because they have to lose only 1 valence electron, they're positive 1, right? So knowing what group they're in will tell you how many valence electrons it has, and then it'll tell you, what charge they'll become when they become ions, right? Because the whole goal is to get that stable octet of electrons. Okay. Now notice the transition metals and some of the heavier metals over here in the p block have more than one charge. Okay. And now remember, we call those metals, we call them MOM ions. What does MOM stand for? Multiple oxidation metal. These are metals that, will sometimes lose 2 electrons or 3 electrons, or maybe they'll sometimes lose 2 electrons, or in some other cases they'll lose 4 electrons. So they could become ions with multiple charges. I don't have to worry about that with sodium. Sodium has 1 valence electron, it'll lose that 1 valence electron and become a sodium plus 1 ion, and that's it. A sodium ion is always plus 1. But these things, they're not gaining or losing electrons to get a noble gas, they're not losing electrons to get a noble gas configuration. They're just losing electrons to get a more stable electron configuration that might not necessarily be the same electron configuration as the noble gases. So iron, like if we look at iron sometimes can become 2 plus, iron can sometimes become 3 plus. That's why we call it MOM ion. It can oxidize to 2 plus, it can oxidize to 3 plus. Okay? It just depends on the situation. Okay? Now, because of that, I need to name an iron ion with a little bit more detail that I don't need when I name like a calcium ion. If I tell you that you have a calcium ion, it's understood that it's calcium 2 plus. Why? Because you know where calcium is on the periodic table. You look at it, it's 2 plus. But now if I said you have an iron ion, right? Well, now the question is, is it the 2 plus iron, or is it the 3 plus iron? Okay, so what you want to know about the MOM ions, which are the transition metals, and some of these. Now, the ones that we're going to focus on are the transition metals and then tin and lead. You need to know that tin and lead are MOM ions, and then anything in the D block except for zinc, cadmium, and silver. So zinc, cadmium, and silver, notice they only have 1 charge. Okay, so they're not MOM ions. But the ones here that have multiple charges, and these metals down here can have multiple charges, they're weird. So anything in the D block except for these 3 right here, zinc, cadmium, silver, and then you have to remember tin and lead, those are MOM ions. And all you need to know right now is if they're MOM ions, that means when we name them, we need a Roman numeral when we name them. And the Roman numeral is the charge. So the way I name an iron 2 plus ion is I have to say iron Roman numeral 2. The way I name an iron 3 plus ion is iron Roman numeral 3. So like if I wanted to name lead 4 plus, because it's a MOM, it would be lead Roman numeral 4. But this ion, lead 2, would be lead Roman numeral 2. Okay? The calcium ion, I don't need a Roman numeral. I can just say calcium because calcium is not a MOM ion. Right? So because I know that a calcium ion is always 2 plus, there's no other alternative to that, I don't need the Roman numeral. But because we know that iron could be multiple charges, I got to tell you which charge it is. Is it the iron 2 or is it the iron 3? Okay. And then just remember, we talked about this a little bit last unit, and again, you'll be responsible for it when we get to unit 4. But like the negative ions, the anions, remember for these, we just changed the ending to "ide." So we don't say nitrogen ion, we say nitride. We don't say phosphorus ion, we say phosphide. We don't say oxygen ion, we say oxide. So what do we call that? Fluoride, chloride, bromide, iodide, instead of fluorine, chlorine, bromine, iodide. Okay? All right. So eventually, we're going to, later on this unit, we're going to get into these periodic trends. Okay? So like, we're going to learn that atomic radius increases going this way across the periodic table, but electronegativity increases going this way across the periodic table. And ionization energy increases going up, but atomic radius increases going down the periodic table. So we're going to define all these things. We're going to figure out what electronegativity is, what ionization energy is, what electron affinity is, what atomic radius is, all that stuff. But that's the next thing that's coming is, which one of these elements has the greater electronegativity, which one of these elements has the lowest ionization energy. And we're just going to memorize the trend, and then based on the trend, we're going to say, oh, well, this element is further up and to the right, so that means it's more electronegative than this element that's further down to the left. Okay? And we'll learn the definitions and why that is, and why the structure of the atom, why the structure of this atom makes it have a low ionization energy, but the structure of this atom makes it have a high ionization energy. And that's what we're going to get into later on this unit. Okay? All right. So again, remember, all that information, but you only get that, right? You don't get any of those labeled periodic tables. This is what you get on your quiz, on your test. That's what you get. So make sure you're doing some memorization. All right? I'll catch you on the next one.